Hi, I'm John Anderson, and this is Enhanced Content for Common Engineering and Technology Courses, Module 7. In Module 7, we're going to talk about composites manufacturing. So we're going to expand on what we talked about in the intro to composites, and we're going to start talking about process design for actually manufacturing composite parts. So let's get started. In the basics of manufacturing, composites manufacturing, we're going to review some material that we covered in the intro to composites. This course is actually set up to be a standalone course, or the three-course sequence in composites manufacturing stands alone. We don't necessarily have to do the intro to composites, and there is some overlap between the two. The best thing is to do the intro to composites. You get a much more in-depth presentation of the basics there. But if time constraints are an issue, then you could use this as a standalone. So we have learning objectives here, and we go through a module overview. It's essentially the process by which composites are made. We've talked about this building of composite parts before when we went through the intro to composites manufacturing. The intro to composites. And basically it is, we take a series of sheets and we lay them up into a laminate in a mold. We apply heat and pressure to this laminate to make it conform very closely to the mold and to cure, and then we do a post-cure, whatever post-cure process is, and then we pull out the finished part. So let's think about some basic rules for manufacturing of composites. First of all, we need to be sure that we put the fibers in the direction where the loads are going to be. And we'll talk a little bit more about this as we get on into this presentation. But remember that most of the strength of a composite material comes from the fibers, and so it's the maximum load can be taken in the direction of the fibers. We need to control the temperature, viscosity, and cross-linking reaction to maximize matrix properties. So what does this mean? Well, we said before that putting together composites is a very process-driven procedure. That is, you have to have process control all the way through to maintain quality. So temperature is important not only in the curing, the cross-linking process, but also in the wetting process. When we add our resin to the fibers, our resin is in a liquid state. Since we've already added the catalyst, or the second part, to the resin, it is in the process of cross-linking. As it cross-links, the viscosity rises, and eventually, as the cross-linking continues, it becomes a solid. So it's very important for us to control the time, and thus the viscosity, the speed of the reaction, and the time, the open time between when we mix the resin and when we actually add it to the fibers, and to control the ambient temperature where we're adding this resin to the fibers. Temperature has an effect not only on the speed of the reaction, but also on the basic viscosity of the liquid. So the lower the viscosity we can get, the easier it's going to be to wet the fibers. And it's very important that we get a complete wetting of the fibers. We want to have the resin flow around the exterior surface of the fibers and to form a close and intimate mechanical bond with the fiber as the resin cross-links. If we don't do that, if we have a high viscosity where we don't get a very good mechanical bond, the liquid doesn't want to flow into all the discontinuities on the surface of the fiber, so that we don't get a very good mechanical bond, then we lose strength of the overall composite structure. Third, we want to compact the composite structure during the cure to ensure that the layers are properly adhering and that the air bubbles are reduced. We want to use vacuum bagging so that we reduce the pressure on the inside of the bag, and the atmospheric pressure pushes the bag down so that we press the gases, both air and any outgassing we might get from the cross-linking of the resin. We want to press that out, get it out of the interior of the laminate material. Any void that we leave in this when we finish the curing of the part becomes a stress riser. And so this is where we start seeing failure in the material, either delamination or cracking or whatever. And the only way that we can control that is through the process. The composites are often a part of assemblies, and so we've got to take care when we're making individual parts that we properly finish the parts so that we can affect the assembly, whether that's co-bonding, whether that's mechanical fastening, or whatever. This is a generic part process flow chart. So we start up here at the top, and this is assuming a prepreg material. So we start up here at the top. We have our prepreg material in the freezer so that we're slowing down the cross-linking and extending the shelf life of this material. Take it out of the freezer, we thaw it out, we take it to cut out so that we're cutting the patterns that we need to fill our mold. And then typically in a manufacturing process, if you go to Northrop Grumman or Boeing or Lockheed Martin or any of the aerospace companies, they'll take all of the parts that you need, all of the cut out prepreg parts that you need, and put them on a rolling cart. And this is called kitting. So you have the instructions, you have any resin that you might need, you have all of the cut out sections of the prepreg material, tape, vacuum bag material, everything that you need is in this kit. So you have it all in one place, and you roll this over to the mold, and then the operator uses that kit to build up the part. Obviously, if you have pieces left over when you finish building up the mold, you have a problem, and you probably want to stop before you put any extra cost into this part. And then next we have a Y here. We have two things coming together. We have our kit that we're rolling up to the mold to start doing the layup. But before we can do the layup, we have to do tool preparation. And this may be cleaning the mold, it may be applying mold release, whatever's necessary to make the mold ready to receive the pieces during the layup process. Once we get it laid up, we'll bag it, vacuum for the vacuum bagging process, and then we'll either put it into a heater or autoclave and cure it, take the part out, trim it up, trim any excess off the edges, and then we'll inspect the part, paint and seal if that's necessary, and then join and assemble this part to other parts and then package it for shipping. Let's talk about cost drivers. What are the pieces that make up the cost of a composite part? Well, if you look over here, just in the fabrication of the basic part, you have approximately 50% of the cost of that fabrication is in layup. Very, very expensive process. And then you have a much smaller section for tool prep, for bag and cure. This is a fairly time-consuming process. For trimming, this is non-destructive inspection, and this is ply cutting. So if you're looking for low-hanging fruit to decrease the cost of your parts, it's pretty obvious where you can look first, this layup process. Anything you can do to automate that is going to drive the cost of the composite parts down. And then, if we look at the total cost, we have to look at the materials, this fabrication cost from over here, plus the materials necessary to make this happen. And that comprises about 50% of the total cost. The other 50% is assembly. So if you think about this assembly process and its layup process, these are heavy, labor-intensive sorts of processes, and that's where our cost really comes in for composites. So our production process, we have some needs there. We need raw material, we need tooling and a mold, we need heat and pressure, and we need a quality control. A lot of this, I just can't say enough about this. The quality control in composites is largely driven by the continuity of the process of making these parts. So let's talk about material considerations. We have fiber. We've gone over this before, so I'll just go over it real quickly. We have three types of fibers: glass, carbon, and aramids. Glass is the cheapest. Carbon has the highest specific strength, and aramids fall, in terms of cost and strength, somewhere in between glass and carbon. The unique thing about the aramids are that they're much less brittle than glass or carbon, and so they have impact resistance. They don't shatter if you hit them with an impulse. So that's why Kevlar is an aramid. Length of fibers, we have short fibers, typically around a 1/2 inch in length. Anything over, I believe it's 3 inches is what's normally, is the length that's normally used. Anything over 3 inches is considered continuous. We have several formats that we can present our fiber in. We have unidirectional tape. We can weave this into a mat. We can present it as a tow or a roving if we're talking about glass fibers, or we can weave it into a cloth. The resin considerations for thermoset resins, this table will give you some of the high points of the different types of resins, of thermoset resins. Typically, all of these have a high temperature resistance, so and they have typically low viscosities. When you first, the base components have low viscosities before they start cross-linking, so it's fairly easy to wet out fibers with this. Thermoplastic resins, they're used less often in high performance applications. High performance being things like structural applications in aerospace, but there is an increasing push to try to use thermoplastic resins in composites more because they're much easier to work with than thermosets. So the primary categories of thermoplastic resins that are used in composites are nylons, polypropylene, PEEK, and PPS. This PEEK and PPS have high, for thermoplastic, they have fairly high operating temperatures and fairly high strength. They're on the upper end for thermoplastics. Nylons fall somewhere in the intermediate range. You can get nylons in a lot of different configurations, and they cover a fairly wide swath of both use temperatures and strengths. Polypropylene is by far the weakest of these. It has the lowest strength and the lowest operating temperatures, but it's also very cheap. It's a commodity type plastic. Fiber orientation, when we specify a composite part in the kit we talked about before, you'll have a set of instructions, a set of engineering drawings. Those engineering drawings will indicate the orientation of each ply by a clock method. So this clocking is referenced off of the mold and gives you a degrees of offset for the direction of the fiber. So we talked about this before. Yarns are bundles of fibers. They're a tow if they're carbon fibers. They're roving if they're fiberglass. We have unidirectional tape, and we've seen unidirectional tape being applied for the Boeing 787 fuselage in the film we watched in the intro to composites. And we have woven, fabric, and matte. We also can get a couple of other things, processes we haven't really talked about yet. We have a process called compression molding, and I have a short film here I'll show you on compression molding.
This program is an introduction to compression molding. Compression molding is one of the most common methods of producing high-volume composite parts and components. These parts and components are manufactured for use throughout various industries, including transportation, electrical, construction, and more. Both thermosets and thermoplastics may be compression molded, with thermosets being the primary type of materials used. The compression molding process typically involves placing a pre-cut, pre-weighed charge of material onto the lower half of a heated mold. The heated upper half of the mold is then lowered rapidly, causing the charge to flow, compressing it to the required density and shape as defined by the mold. With some presses, the lower half of the mold moves upwards, forcing the mold halves together. Once the material cures under the heat and pressure, the press opens, and the compression molded part is demolded, typically with the assistance of an ejector system. After demolding, any flash is removed. This is done either manually or through the use of deflashing processes such as abrasive blasting. Several factors influence the molding conditions during compression molding.
So the raw material for compression molding is typically either SMC or BMC, sheet molding compound or bulk molding compound. And I have another video here that shows how we make sheet molding compound. This is a diagram of the process by which sheet molded compound SMC is made. We have two rolls of carrier film. This is like a release film. So there's one here and one here. What we're going to end up with is the resin and glass, or resin and fiber, actually in between those two layers. So you'll have a sheet that has a carrier film on top and a carrier film on bottom with the resin and fibers in between. So we unroll a carrier film over this roller onto the bed of a conveyor, and we put resin paste, we meter resin paste. This is like a doctor blade or a dam, so that we put a glob of paste, to use a technical term, and we smooth that out so that we end up with a uniform layer of resin paste. We take typically glass, fiberglass, and we'll take continuous strands and run them through a chopper. This is a chopper blade. So the chopper blade cuts this into short staple fibers, and we drop those fibers onto this moving resin paste on top of the carrier film. And the idea is that you get a fairly random orientation of the fibers coming down, so you have pretty much uniform properties in the sheet. That is, the same tensile properties in all directions. And then we go forward, and the second carrier film unrolls off of this roll, I should say. Through this roller, we put some more resin paste on the inside, what's going to be the inside of this carrier film. Again, we have a doctor blade there so that we meter off a known thickness. The resin is now on this side of the carrier film, so we can still run the other side across rollers to control the direction. We bring that down into a nip point here, where we're pressing this top carrier film onto the combination of the resin paste and the chopped glass. And so we have another layer. We have a layer of resin paste, a layer of chopped glass, and then a layer of resin paste. And this whole thing is sandwiched between two carrier film layers. So then it goes through a series of compaction rollers, or a compaction belt here, that squeezes out all the voids and gets us to a uniform thickness. We go through another nip point here like a calendar, and then we wind this up onto a roll. And that is, turn this animation on, that is making sheet molded compound, or sheet molding compound, I should say. And the last of these is bulk molding compound, again to feed primarily compression molding, the compression molding process. So the bulk molding compound, what we're doing is making a dough. This is also called dough molding compound, sometimes DMC. Basically, we have a resin reservoir, so we're feeding in resin, and we're adding to it catalyst and then pigmentation if we need it for color, or any additives in there for things like oxidation resistance. So then we take that resin and we feed it down to a high viscosity mixer, or high shear mixer it's called. We're going to add in to that some fillers. This is typically inorganic stuff. It is limestone or something else, talc, to give it bulk properties, to give it a little extra stiffness, and to increase the thermal properties primarily. And then we use glass reinforcement to add strength. So we take all of this, we put it in, and we mix it up, and we end up with essentially a pre-preg in a bulk compound. So it's starting to catalyze, it's starting to cross-link, it's been catalyzed, it's starting to cross-link, the viscosity is starting to go up. We mix it, and then we take it out and lower the temperature to arrest that cross-linking. So we basically have a glob of pre-preg material with glass reinforcement in it. Glob is also a technical term. Now there's some things to consider here. This shear mixer is a pretty sophisticated piece of equipment, although it's sort of a blunt force instrument too. As you add shear in here to mix this all of this stuff together, you're also adding heat into the mixture because of the friction that you're creating as you mix this. So typically these have cooling jackets on the outside to try to control the temperature, and you do this in a batch. You put in a batch of resin and fillers and glass fibers, you get the mixture right, and it may be 50 pounds of BMC that's in here. You mix it up, you take it all, you dump it out of a door on here, and then you put another batch in. Well, this concludes Module 7, which is the first of 2 modules on composites manufacturing. In the next module, we're going to expand this coverage of composites manufacturing. We'll start talking about some tooling and processes. And so, hope to see you then.